In this session, we will discuss some properties of electric conductors, force acting on the surface of the conductor and idea of capacitors. First, we will discuss about electric conductors and their basic properties. An electric conductor has a very large number of free charges. When an electric field is applied at the conductor, charges inside the conductor reorient themselves so that the two ends of the conductor acquires opposite charges. The positive charges move in the direction of applied field, while the negative charges opposite to it. The shift in the charges within the conductor produce an electric field inside the conductor which is opposite to the applied field. Since the conductor contains very large number of free charges, the separation of the charges inside the conductor is continued until the net electric field inside the conductor becomes 0. So, we have the expression E inside is equal to the electric field plus the electric E dash, which is equal to 0. So, we will get it as E is equal to minus E dash. From the Gauss's law, we know that del dot E is equal to rho by epsilon 0. So, applying the equation del dot E in is equal to rho by epsilon 0. Rearranging the equation, epsilon 0 del dot E n is equal to rho, E in will become 0 and epsilon 0 into 0 is equal to rho. That is, the charge density inside the conductor is 0. So, we can say that if the electric field is 0, the work done in moving a charge inside the conductor is also 0. And the work done has the expression W is equal to minus integral a to b E dot dl, which is equal to 0. It is obvious that as no work is done inside the conductor, there will not be any change in the potential when a charge is moved from one point to another. That means, the potential inside the conductor is a constant, that is V A minus V B is equal to 0, that is V A is equal to V B. By boundary condition, we know that the potential is continuous through the boundary. Just recalling the boundary condition, V up minus V down is equal to 0. If the potential inside the conductor is 0, then the potential over the surface of the conductor is also 0. That means, the surface of the conductor is an equipotential surface. Also, when an electric charge is given to a conductor, it cannot penetrate into the conductor as there is no field inside the conductor. It can remain only on the surface of the conductor. So, the charges given to the conductor get uniformly distributed over the surface of the conductor, keeping the surface of the conductor equipotential always. The work done in moving a unit charge on an equipotential surface is always 0. W is equal to minus integral E dot dl is equal to 0. Since electric field E or dl can't be 0 and the work done must be 0, then the only possibility is E not equal to 0, dl not equal to 0 and the angle between them must be 90 degree, that is cos theta is equal to 0. So, theta becomes 90 degree. So, we can conclude that outside the conductor, electric field is perpendicular to the surface of the conductor. Induced charges in a conductor and effective force of interaction. When a charge plus q is kept near the conductor, equal amount of negative charges are induced on the nearer side of the conductor, while equal amount of positive charges are induced on the other side. By Coulomb's law, F is equal to 1 by 4 pi epsilon 0 plus q into minus q divided by r square into r cap. Since force is inversely proportional to square of the distance between the charges, it is clear that the force of interaction between external charges and the induced negative charges in the conductor is greater than the force of interaction between the external charges and induced positive charges inside the conductor. So, there will be net force of attraction between external charges and electric conductor. Electric conductor with a cavity having a charge. We know that electric field inside a conductor is 0. So, when a positive charge is kept inside the cavity, negative charges will be induced on the inner surface of the cavity. Consequently, positive charges will be induced on the outer side of the conductor. So, the presence of any kind of charges inside the conductor will be communicated to the outside world through the presence of same kind of charges on the outer surface of the conductor. Consider a Gaussian surface that encloses the cavity inside the conductor. Applying Gauss's law, integral E in dot dl is equal to q enclosed by epsilon 0. So, we know that E in is equal to 0, q enclosed by epsilon 0 is equal to 0. Therefore, q enclosed is equal to 0. From Gauss's law, it is clear that the total charge enclosed by the Gaussian surface is q enclosed is equal to q plus q induced is equal to 0, that is minus q is equal to q induced. Safety shielding inside the cavity of a conductor. Consider a conductor as shown in the figure with the cavity inside. A closed path is shown which is partially inside the conductor and the remaining part inside the cavity. So, the integral in the equation can be written as integral E dot dl is equal to integral E in dot dl plus integral E cavity dot dl, which is equal to 0. So, 0 plus integral E cavity dot dl is equal to 0, which means that electric field inside the conductor is 0. So, integral E cavity dot dl is equal to 0. So, E cavity will become 0. As the intensity of the field inside the conductor is 0, the electric field inside the cavity must be 0. That is, the field inside the cavity of a conductor is 0. This is why we are safe inside a metallic car. As there is no field inside the car, charges will not flow into the person sitting inside a car and is saved from electrocutting during thunder and lightning. Force acting on the surface of a charged conductor. We know that from the previous section, the electric field E inside the conductor is 0. Following the boundary condition for E changes by an amount of sigma by epsilon 0 through the surface. So, here E is equal to E out, which is equal to sigma by epsilon 0 into n cap. In terms of potential, dou V by dou n is equal to del V dot n cap, where n cap is any unit vector. But we know that electric field is the negative gradient of potential. So, E is equal to minus del V. Therefore, dou V by dou n is equal to minus E dot n cap. Comparing the equation, dou V by dou n is equal to minus sigma by epsilon 0 n cap dot n cap. We know that n cap dot n cap is equal to 1. So, the equation becomes dou V by dou n is equal to minus sigma by epsilon 0. So, from the expression of E or from the expression of dou V by dou n, the charge density sigma can be calculated. And the charge density means it is the surface charge density. Now, if Q is the total charge residing on the surface of the conductor, then the force acting on the conductor F is equal to Q into E surface, where E surface is the electric field at the surface of the conductor, but E surface is average of E out and E in. So, E surface is equal to sigma by 2 epsilon 0 into n cap. Therefore, the force F is equal to Q into the charge Q into sigma by 2 epsilon 0 into n cap. Also, we have learned that Q is equal to sigma into A, where A is the area. Now, the F becomes F is equal to sigma A into sigma by 2 epsilon 0 into n cap. So, the force acting per unit area of the surface of the conductor is F by A and is also called the electrostatic pressure on the surface of the conductor and has the expression P is equal to F by A, P is equal to sigma square by 2 epsilon 0. Capacitors. Capacitor is an arrangement of conductor used to store electric charges. Let a capacitor is formed by two conductors as shown in the figure. If we use the charge on one of the conductor, then the electric potential experienced by the other conductor at a distance d is given by V is equal to Q by 4 pi epsilon 0 d. For a given capacitor, the distance between the conductor is kept constant. V is proportional to Q and the constant of proportionality is called capacitance. V is equal to C into Q. Its SI unit is farad, which is represented by the letter capital F. Now, we can derive the expression for capacitance of a parallel plate capacitor. Consider a capacitor made up of two plane conducting plates of area A and the distance between them is d. Now, consider a charge Q is given to the left plate, then minus Q charge will be induced in the inner side of the right plate and consequently plus Q charges on the outer side of the right plate. As the outer side of the right plate is earthed, plus Q charges are pushed to the earth. Now, the two plates are charged equal, but with opposite charges. If we assume that area of the two plates considerably large, then the system of two plates acts like an infinite sheet kept parallel. We know that such a system has electric field existing only between the plates, which is given by E is equal to sigma by epsilon 0. Now, in terms of electric field and potential, E is equal to V by d, and V is equal to E into d, V is equal to sigma by epsilon 0 into d. But we know that the capacitance of the capacitor is related with the charge Q and V as C is equal to Q by V. Recalling the fact that for a charged sheet of charge density sigma and area A, the total charge is given as Q is equal to sigma A. Rearranging and substituting the values for Q and V, C is equal to sigma by A divided by sigma d by epsilon 0. On mathematical calculation, the sigma will be cut off. So, C is equal to epsilon 0 A by d. So, the capacitance is purely a geometrical entity and it which depends upon area of the plate A and the distance between the plate d and also the medium between the plates. Suppose any dielectric medium for permittivity K is introduced in between the plates, then C is equal to K epsilon 0 A by d. So, the capacitance is increased by K. Energy stored in a parallel plate capacitor. Consider a parallel plate capacitor as shown in the figure. Capacitor is charged by transferring charges from one plate to another. If Q is the charge transferred at a particular instant, then the potential is given by V is equal to Q by C. Further, the charges are to be transferred by doing work against the potential developed. The work done is given by if dq is the small amount of charge transferred against the potential V, then the small amount of work done is given by dW is equal to dq into V. But we know that for V we can substitute q by c. So, dW is equal to q by c into dq. So, the total work done is from 0 to capital Q, W is equal to integral 0 to q dW. On integrating, we will get W is equal to 1 by c into integral 0 to q capital Q q dq. So, W is equal to 1 by c q square by 2, or can be written as W is equal to q square by 2 c, or was substituting the value of q or for the c, you can get another expression for work done, W is equal to half c V square. V is the final potential difference between the plates after transferring the required amount of charges. This much of work is stored as the potential energy of the capacitor. So, in this session, we discussed the concepts of basic properties of conductors, induced charges and net effective force of interaction, electric conductor with a cavity having an electric charge, safety shielding inside the cavity of a conductor, and finally, the force on the surface of the conductor. And last, we discussed about capacitor and the energy stored inside the capacitor. Hope you have enjoyed the session. See you next time. Until then, goodbye.